Okay, so I wanted to record another video to clean up some problems and mistakes made in the previous one. So let's get started. First of all, I want to clarify that after further checking how the system works under the hood, it has become pretty much clear that it is indeed a nav mesh and not some weird node-based system. The whole confusion comes from, well, this text I generated with my JSON generator for my XMB decompiler, right? But these are the variable names in the decompiled code, right? And the confusion comes from the whole vertex A, B, C, neighbor A, neighbor V, cost AV. It pretty much made it seem like the nav mesh, quote unquote, was actually more like a grid of points, and the costs that we were computing were the cost of going from A to B rather than the cost of traversing from one polygon to another through the edge AV, right? So after obviously making the previous video on showcasing how it works, it's clear that it is just a regular nav mesh. It becomes clear what each of these properties means. But I did say that I was kind of confused in the previous video and maybe explained some stuff that may be a little bit wrong. So I wanted to make this video to clean this up and also fix an issue in here. So this is the current code right now for computing the costs of traversing, which it's made to be as efficient as possible and give the best result possible by making use of the fact that basically each and every single one of the polygons within this system are basically just that. They are triangles. So since they are triangles, we can make a lot of assumptions. Now, the original code was thought of as if everything was a grid of nodes connected, and you would be making something like BFS or A star to search through it. And the costs would be computed as the positions of each vertex from an edge, subtracted from each other, and basically getting the distance. So what this means is basically I would compute the cost as the distance between the vertices on each edge, thinking that the edges were the connection between vertices and that the vertices were the nodes. And that's clearly wrong. I mean, in this case, it would have made sense if that was the case, but since it's not the case, we're basically computing the wrong thing, right? So basically, we would be saying that the longer that the edge is, the more costly it would be, and that would make sense in a grid system or a tree with nodes. But this uses an actual nav mesh. So what we would be saying is that the more open an area is, the more costly it is to get to it, which doesn't make any sense. So I basically changed the implementation to say calculate the middle point of the triangle and then get the distance. I'll calculate the middle point between all of these edges, right? And then just get the cost as the distance between the midpoint and each of those edges. That way we would make sure that we would be getting a somewhat good and cheap approximation. I mean, even with the wrong costs calculated, the AI was already moving pretty nicely through the map. So this should only improve edge cases, like when the goblin was getting stuck on the corner trying to get to me. Pretty much some of that stuff would go away using this system. So now let me just make a simple explanation, right, that I want to make about the difference, because some viewers might also be confused if they come especially from engines where nav meshes don't exist and everything is based on nodes for locations and traversing a tree of nodes, and there's like some sort of margin of error to define how far away the bots can go. So we go back to the triangle that we had before. We would have our vertices basically, right? And we can say that this right here is a equivalent to one of our nodes. This triangle right here is the equivalent to one of those nodes in that system, right? And it has its vertices A, B, and C, right? Which would have its own coordinates. We're not gonna even bother writing their indices because we don't care about that from this point of view. We just care about the fact that we've got a triangle, which we're gonna name T0, right? And we've got these edges, which would be the edge AB, VC, and CA, right? So those are the edges that connect those points for this triangle right here. If we have another triangle here, for example, right, what we have is, imagine that this right here is A, this is B, this is C. It could be in any order actually, but this is the one that we've imagined for this occasion, right? And this would be T1. What this means is that the edge from the point of view T0, which is AB, right? The edge AB, which from the point of view of T1 is actually CA, right? Is the edge that separates these two triangles. And this is how we determine how to move from this triangle to this other triangle. This we could imagine as being the nodes N0 and N1. And this edge right here would actually be represented like this. And these edges, since they don't connect with any other triangles, would basically be in this case like no connections at all. If you think about it, like being a system with nodes, right? But it's more powerful because we encode more information. If we have a room with a floor that goes somewhat like this, with this nav mesh, which has these vertices, we've encoded a lot more information than with these nodes, because with these nodes we would just have one pointing here and one pointing here and some value of cost for going from one to another, which doesn't really tell us anything about the shape of the room. So we would have, for example, a system where we have like a distance in the bots where we say you can go at most 6 units away from this point, right? And they could just fall off the platform and die. And this is very common in many game engines, and that's actually why some engines like that use waypoints like this one right here, such as the Quake engine, make use of brushes, special brushes that tell the AI not to cross those paths, right? So that's why the nav mesh is more powerful and it's just better overall, right? Another point is that since the polygons themselves are just the nodes, if we have a giant space, we can, rather than defining lots of small points as nodes where we would say that the AI is capable of traversing between them, we could just go ahead and define 1 point here, 1 point here, 1 point here, and 1 point here. And then we get a quad, which in many systems is actually a perfectly valid nav mesh shape. It has to be a convex shape, and I'll explain why in a while. In the case of Magicka, the only shape that exists for the nav mesh is the primitive triangle, right? That's the only primitive that is allowed. So we have only one node and another one, 2 nodes in truth, right? So what is the property that is so good about this? Well, the thing that is so good about this, right, because in this case the cost of going from one triangle to another is this edge right here, so we've got exactly the same model as here, but we've got some extra steps. And you say, why? Well, we can first of all reduce the number of nodes used for larger areas, and second of all define the shape of the room, and third of all we can actually make a lot of optimizations, right? So let's imagine we have a room that goes somewhat like this, right? That is small room here, a bridge in the middle, and another room here, right? And if this was divided with nodes or squares, like in a tile set map, right, like in Game Maker or RPG Maker or whatever, the AI would have to go in fixed intervals. So we will have a bunch of fixed squares, something like this, right? And these squares would be the valid positions where you would place the nodes through which the AI can actually traverse. And this would be a problem, because let's say that, for example, we've got our player in here and we want the bot who is here to reach the player. Well, first of all, if we are using BFS or anything like that, it would explore here, explore here, explore here, explore here, then explore further, go exploring everywhere, wasting a lot of power until it flooded this room and it kept going here, right? It would have to do a lot of steps to just do a fucking straight line, right? And if we use a star, in this case, it would just use the heuristic of the Manhattan distance between this square and this square, and it would just go here, 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 right? And it would be much cheaper, but it would still have to compute this path in case that there's some obstacle around here or whatever, right? So having to recompute this constantly gets pretty expensive the more entities you have, right? And it gives you fixed precision, like fixed squares where you can locate your character. If you allow it to go off from the path, it may fall off from the bridge, or it may differ a little bit and hit the corner until it eventually realizes that its radius is outside of this square, and it just corrects back to the closest square, whatever, right? Like, it's not really the best system for a 3D environment, right? This is perfectly valid for 2D games, but not for 3D environments, right? So it makes more sense if we go ahead and change this system to make use of a nav mesh. So we define our vertices here, 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 maybe a few vertices here, some here, 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 and here. And what our mesh would look like, right? We could also probably put some in here to make it easier to support these edges. We will have something that looks like this. Let me draw in red, for example, right? We could have something like this. And, well, we wouldn't really have this as primitives, so we have to triangulate. So, for example, let's imagine we triangulate like this or something, I don't know. Whatever, who knows? Anything goes, right? This could be what our mesh look like, and the same thing on the other side, right? As an example, it doesn't have to be this, but it could be that. So our vertices exist in these places. Actually, we have way many vertices than nodes, and if you think about the total number of polygons we have, it's way less. These are the equivalent of the nodes in the previous system, right? And the edges are the edges, but rather than connecting this vertex and this vertex, we connect this and this, right? So we have much less information to store in memory for the same amount of precision and information. Actually, it becomes easier to compute and way faster, and it actually allows you to encode far more information within a smaller amount of memory, because you're going to take up more space in memory for each node, because this whole polygon is a node. But since this whole polygon that takes up all of this space is a node, you can afford to encode all of this information, right? Because in total you're gonna have way less nodes, right? So since you're gonna have way less nodes, you're gonna end up being able to use more of this memory that you have gained now to encode more extra information that's going to be extremely useful to make things even faster, because you're going to simplify the calculations. And how do you simplify them, you may ask? Okay, imagine that the player is located here. Let's draw them with, I don't know, brown. The player is here and the bot is here, right? And what the bot does in this situation is literally say, okay, I am in this position right here and the player is here. This is my origin position. This is my target destination, right? This is where I start. I start in this polygon right here, okay? And this is where I start, and this is where I'm gonna end. So first of all, rather than computing with a star the path going through these edges right here, we are going to do something way simpler. We're gonna say, is there a way to trace from this polygon right here to my target polygon a straight line that doesn't intersect with anything, right? And yes, we can. We draw this straight line, and what it does is every time it intersects with one of these lines, it will say, I've intersected. Am I still inside of any polygons? And it will go, yes. Okay, continue going. Intersect, am I still inside of a polygon in here? Yes, I am still inside of valid nav meshes. Intersect, am I still inside of a valid polygon? Yes. And apart from checking if you're still inside of a valid polygon, you also check, is this my target polygon? And if you say yes, then you don't need to compute anything else. We finished already. We don't need to do any further steps. The bot knows that they can just walk in a straight line to their target, and that's it. They are done with that. But let's imagine that they are not located in that way. The player is, for example, here, yeah, and the bot is here. They are going to trace this straight line here. And the first thing they're going to do is go ahead and say, when I intersect this wall right here, this edge, I'm still inside of a polygon. And how do they know if they're inside of a polygon? Well, since it is very easy to calculate intersections with convex shapes, which is what we mentioned up here before, right? It is trivial to compute when you intersect with a side of the triangle, and you can pretty much just get, yeah, intersected with this edge right here, and you go ask the data structure, hey edge, what is your the other triangle that you're pointing to, which we have right here. We say, well, neighbor A is this one right here, okay? And we said that in Magicka specifically, in this case I don't have but when we have the maximum value for an unsigned 16-bit number, that is the equivalent within Magicka's code to say null, that there's no triangle connected through that edge, right? So we just say null in this case as a higher level overview, because it could be implemented with pointers or indices or whatever, right? We just say this value points to nothing, there's no triangle here, and we instantly know that we can't make a straight line for our target, right? And we go, okay, since we know that we cannot go in a straight line for our target, what do? We make a star. That's it. We do a star. We look at the edges around us. We see which one has the smallest cost, and we go through them. Obviously, if this were to have the smallest cost, because this is the center and we're computing it from the center, for example, right, it would probably be this one in this case, but whatever, let's imagine that this one would be the one with the smallest cost. It would try to traverse it and say there's no triangle here, check the next valid one, because it's a star, so it's still got the open list, only that the edges look different, but they still connect the things in the same way. So we go through here, we compute that we gotta go here, we gotta go here, and from here we could even just finish the computation to make a straight line, or just keep using a star, right? And we finish saying that we have to come here, and the bot could say that they have to go here, and they have to go here and here and here and then here, or they could interpolate this whole path, whatever. That's the implementation under the hood of what the bot does, right? So that's why nav meshes are so much more powerful for 3D environments, right? That doesn't mean that the node system is useless, right? But this is very useful, right? And with this change that I've done right here, okay, where we have computed the cost differently, we're going to see a big difference in how the bots behave, and it's going to greatly improve their behavior. Now, yeah, that's all I really wanted to say, to be honest. Not much else for me to say in this case, so yeah, thanks for watching.